in this section. I will continue. Uh, so, so for the mid exam, I told you you will get up to about uniform plane waves. So, right, in the end exam, you will get some extra. I mean, in the end exam, you will get all the content you have covered that that are related to electric field, magnetic field, uniform plane waves, and Maxwell, uniform plane waves, transmission lines. And if I feel like, I will add about antennas also. Right. So these are the sections that will come to your end exam. Okay. So so currently I'm in this stage. I will be discussing about the transmission lines and the antennas in this hour. Okay, so up to uniform plane waves, I will be asking questions in the mid exam. So these two content are important for the end exam. Okay, so we are going to discuss about the transmission lines. Okay, so transmission lines help us to transmit energy, transmit signals from one place to another location. Okay, so I will talk about transmission lines. So what are the transmission lines? What are transmission lines? So transmission lines are basically two conductors, right? Basically two conductors that has a separating or insulating material in between. Insulating material in between. Okay, so if you can't read this, let me know. Right, so insulating material in between. So so there are two conductors, the top conductor and the bottom conductor. The top conductor and the bottom conductor. Okay, so most of the time the top conductor is used to used as the top live plane. Bottom conductor used as the ground plane. So with reference to the ground plane, the top conductor's current and voltages vary. So so these kind of conductors are used to transmit waves, electromagnetic waves, from one point to another point. So so we have a location where we generate the electromagnetic waves. So that location is somewhere, let's say is in a generation point, right? So it could be an antenna, it could be a power distribution plant, right? Sorry, it could be a base station. Could be a base station where the electromagnetic waves are propagated, generated, or it could be a power station where the electromagnetic waves are used to transfer the power. So so power generation plant. So in either of these two situations, we have an alternating power supply, and the alternating current and is generated, and the electromagnetic wave is generated. So the produced electromagnetic wave must be transported from one location to another location. So from, let's say, we want to transmit the energy from the location A to a location B using these transmission lines. So we want to transfer the energy from location A to B. So once we are trying to transmit the energy, we face some difficulties and some differences than the usual case where we are sending low frequency signals. Okay, so in this electromagnetic domain, we are sending signals with high frequency. Okay, so we need to use special or specific transmission lines to transmit electromagnetic waves. Okay, so we are trying to send high frequency signals. We are transmitting high frequency signals. High frequency EM waves. Okay, so we are transmitting high frequency EM waves in here, right? So the wave frequency could be in a range where the physical dimensions, right? So the range of frequency or the range of wavelengths, the wavelengths that we consider here in our range of wavelength in the EM wave could be very similar to the physical dimensions of the circuits or physical dimensions of the transmission line. Okay, so what I mean is that if we consider a scenario where we are sending high frequency signal, then the wavelength of that signal is very low. Okay, so if the frequency is high, the wavelength is low. If the wavelength is low, sometimes the this wavelength could be in certain, like 1 millimeters, 1 centimeters range. Also, the physical dimensions of the transmission line could also be in that range. Okay, so in case where we have cables or transmission lines of the width of 1 centimeters or 1 millimeters, then we say that the physical dimension of the transmission line is almost equal to the wavelength of the EM wave. Okay, so this happens especially in microstrip designs or the circuits. So I will explain what microstrip is. So basically, the antennas or the systems or the circuits that we use in our phones, in our smart phones, has transmission lines of 1 millimeter thickness. So if we take, for example, like the circuit inside the phone consists of multiple circuits, digital circuits that contains processing units, storage units, and they will also have a certain antenna, right? So they will have a certain antenna, and those antennas will propagate the signal from the phone to the other areas. So if we take the antenna like this, the line that is connecting the antenna to other components in the circuit is a transmission line. It is we call as T line. So these lines that connect the components in the circuit to the other components in the circuit are known as transmission lines. So these transmission lines are available in PCB circuits, right? So in these PCB circuits, we can see these transmission lines. So these transmission lines are having dimensions of in the range 1 millimeter, 1 centimeter, and so on. So the dimension is considerably low. It's in the range of millimeters, centimeters. In that case, the frequency of the signal that we are sending is also in that range, millimeter, centimeter. Now, because of that, we need to consider that also into effect in order to design the transmission lines. So, so we normally consider uh, I mean that if when we are designing these transmission lines, if there's even a very small fault in our design, then sometimes the transmission line might not work properly. Okay, so because the wave is also in that millimeter centimeter range, and the transmission line is also in that range. Because of that, the precision of the design should be very high to get the output that we need, right? So when we are designing transmission lines, we need to be very precise about uh, the the dimensions of the transmission lines. We need to be very precise with the dimensions of the transmission lines. Okay. So I will show you some transmission line figures. So transmission lines are found in these kind of circuits as well. These are not the only transmission lines, but I'm showing these transmission lines because I think that these transmission lines are very much used in our day-to-day devices that we use, such as phones, computers, any other home appliance where we have PCB circuits. So if we take, for example, these lines that we have in here between these components are all transmission lines. In order for us to design these transmission lines, we need to discuss about the width of these transmission lines and also the dimensions of the transmission lines, such that the transmission of the signals are happening accurately between the components. Okay, so this is also a clear figure about these transmission lines, or these lines are clearly the transmission lines. So these are the transmission lines. We have in PCB these transmission lines. So these are the lines. So so this is useful in PCB circuit, and so therefore I mean, since PCB is used in multiple scenarios, transmission lines can be seen almost everywhere. Also, we have this figure. So we have a certain transmission line here that we denote using this rectangle. So this part is the transmission line part. The part where we have this straight feed line, we call as the transmission line. This is the transmission line. So in the actual circuit, we have the transmission line like this. So the transmission line is going inside the this component, which we denote as the rectangular microstrip antenna. So this rectangular component is the microstrip antenna. So you can search in the internet about further antennas that are used in phones and all. You can see that we have antennas designed only on this kind of a like a PCB circuit, and this is the antenna that we have. This is the only thing as the antenna. We don't create antenna using metal conductors. We create it using some copper, some copper microstrip fabricated onto a PCB board. Okay, so copper or some other material that we use here, we can use to create this antenna by just fabricating that antenna onto a PCB board. Okay, so another thing is like you can see in this diagram, we have this part, the top conductor. We have the top conductor here, and we have the bottom conductor here. The bottom conductor is the ground plane. Okay, so when we see from the above, we can't see the ground plane, but it is available at the bottom of the PCB circuit. So the top conductor is given by this microstrip transmission line and the patch antenna. So this is the part where we have the rectangular patch antenna. This is the part where we have the transmission line. So this is the part where we have the transmission line, right? So the transmission line top conductor is this one. Transmission line bottom conductor is given by this conductor in the ground plane. Okay, so these are the places where we use transmission lines in a very like in a frequent manner. Apart from that, we can also transmit electromagnetic waves using coaxial cables. So the coaxial cables are used to transmit the electromagnetic waves. So basically the coaxial cables can be connected to antennas, which we place in roofs, for example, or in buildings, on top of buildings where we set up antennas. We can connect our antenna feed point to the coaxial cable. So one part of the one conducting like one conductor, either the top or bottom conductor can be connected to one arm of the antenna. So if we have an antenna, we will have two arms, the first arm and the second arm. So let's say this is the first arm. The first arm of the antenna is this one. This is a metal conductor, which is placed vertically upwards. And then there's another metal conductor, which we call as the second arm. And then we connect the first arm to one conductor, second arm to another conductor. Like this inner conductor is connected to second arm. First arm we can connect to the outer conductor. Likewise, we can connect the coaxial cable to an antenna. Okay, so we can have an antenna with two arms like this, and we can connect the power, the antenna to the power cable or the supply cable, which is the coaxial cable. Okay, so that is basically how the transmission lines are connected to a certain load, certain equipment. Okay, so the antenna is the load in here. So we will take antenna as the load, right? So once we connect the coaxial cable to antenna is the load, coaxial cable is the transmission line. So we will consider this kind of example once we are studying about transmission lines. So transmission lines are terminated at using at a certain load. If you have any questions, you can ask. So I was discussing about the transmission lines using this diagram. So you can consider that this transmission line is the one that I showed you in the diagrams. All those transmission lines have a top conductor, a bottom conductor, and they are connected at the end, at one end to the power supply. So this is the power supply, or the place where we generate the electromagnetic waves, right? So in this place, alternating current is produced, and because of that alternating magnetic field is produced, and like a chain of events, electromagnetic wave is produced. The produced electromagnetic wave is transmitted through this transmission line and delivered to a certain load which is connected at the end. So the load I will denote using a certain impedance. So the load I will connect at the end of the transmission line. I will connect it like this. The load, I can take it as maybe the antenna, right? Because I think it is very simple to understand the connection to a certain antenna and why we need to transmit uh, power to an antenna. I think that is easy to understand. So therefore, I connect a load of antenna to the end of the transmission line. So the load of the antenna will have certain impedance. Okay, this load will have a certain impedance, and the transmission line will also have a certain impedance. So once we have this kind of scenario, the impedance will have to be matched, right? If we do not match the impedance between the transmission line and the load impedance, then problems occur, right? So problems means the power losses can occur, and therefore we might not be able to deliver the maximum energy through our transmission line to the load. Therefore, the main goal of our transmission line study, the goal of studying this transmission line is to understand how we can connect a transmission line to a certain load such that the power loss is minimum, and we can get the maximum energy out of this transmission line. Okay, so the goal is to design a system, design a transmission line that can deliver maximum power um, to the load. Okay, right? So designing this kind of a transmission line involves something called impedance matching. So we need to match the impedance between the transmission line and the load impedance in order to maximize the power delivered to the load. Okay, so that is the basic, idea about the transmission line. So before, discussing about the impedance matching, I will explain about the parameters of the transmission line, and I will explain about how we can define the impedance of the transmission line and how we can find the impedance at any point in the transmission line, and those things. Okay, so those are the parameters that we will use to match the impedance of the transmission line to the load. So the final goal is this one. But in order to reach this goal, we need to understand the impedance of the line. We need to understand the impedance of the line at any point in the line, right? We need to understand the transmission line impedance, and then we need to understand how the electromagnetic waves will behave inside this transmission line. So inside this transmission line, the electromagnetic waves can hit the I mean can hit the load and can get reflected, so reflections can happen. So based on the reflections, we define that some part of the wave is getting reflected and there's some power loss, and we can define the power loss. So apart from that, by defining the power loss, we can determine whether the transmission line is good or not. And if it is not good, we can do some additional work to match the impedance to the load. So in doing the impedance matching, we have different methods that we can use. So those different methods can be used to match the line to the load. So impedance matching can basically be done in different manners. So I will discuss about basically matching types, such as quarter wave transformer matching type and quarter wave transformer matching type and stub matching type. So those two things I will mention briefly, and I will just mention how those matching types actually work. Also, I will, under stub matching, I will mention to you something about the Smith chart, where the Smith chart is used to determine the stub matching procedure. However, I will just mention to you how to use a Smith chart, which would be sufficient for you to do the impedance matching later, right? So how to use a Smith chart, I will explain, but matching part, I won't explain much. I will just give a brief introduction. The Smith chart is useful tool to do the stub matching. So the parameters inside the Smith chart, I will inform you so that you can use it in the future to do any kind of impedance matching or any kind of impedance understanding about the transmission lines, or any kind of basically transmission lines in the electromagnetic wave applications. So I will just introduce concepts related to Smith chart as well. So that is basically what I will be discussing under transmission lines. So first, do you have any questions? The load can have both resistance and the complex, impedance. So therefore, it is a complex load. It is a complex load. It can have both the resistance and the susceptance. Sorry. Yeah. So I mean, there are a lot of things that that I can cover under transmission lines. So I mean, anybody can cover under transmission lines. So once you refer the any kind of reference books, you can see that transmission lines can be denoted. Mathematically using a circuit. So that part I think I will just mention to you briefly, but I won't go into the details of it. So I will mention to you briefly regarding the I mean transmission lines and its circuit representation. Okay, so circuit representation. Of a transmission line is so the circuit of a transmission line now, first and foremost, transmission line, let's say it's a very long, like a long line. So there we will consider that we are considering only one cross section of this transmission line. We are considering only one cross section of this transmission line. Okay, so this small cross section that we are taking, let's say, is delta Z. Okay, so the wave is propagating in the Z direction. Wave propagation happens in the Z direction. So the wave is traveling through this transmission line, and this transmission line top conductor is this one, the bottom conductor is this one. Okay, so somewhere earlier there was a power supply supplied to this transmission line, and some electromagnetic wave was propagating inside this transmission line. So the cross section of this transmission line, we are assuming to be uniform throughout. So we are assuming that the cross section of this transmission line is uniform throughout. Of the transmission line is uniform throughout. So therefore, we take delta Z part of that transmission line, and we consider that same behavior or the parameters or the features in that delta Z part, or that small part of the transmission line, is available in every part of the transmission line given here, let's say. Right, so this transmission line is composed of multiple delta Z components. There are multiple delta Z components that this transmission line is composed of. So that all that delta Z components are equal to each other. So studying only one delta Z component is sufficient for our calculations. So we are only going to take a delta Z length of this transmission line, and we are going to study that. Okay, so we will take that delta Z transmission line section. Okay, I will draw that. So that part I will draw in here. So for a length of delta Z, the transmission line can be denoted by a series resistor, series inductor, and a parallel resistor and a parallel capacitor. So the series resistor we denote as R, and the series inductor we denote as L. The value of the inductor is denoted as capital L. The value of the parallel resistor or the shunt conductance we denote use as G, and we denote the parallel capacitance as C. So R in here is the series resistance, which is denoted using omega, and this R is denoting the resistance per unit length. So delta Z length, I mean, we considered this small section to be of delta Z length. Delta Z denotes a very small length of the transmission line. So it is equivalent to the unit length of the transmission line. So the value of R in here, which is related to the resistance available in this delta Z distance or length, is the series resistance of that length. And then its unit is given by ohm over meters. So the value of L, the inductance value is given as the series inductance. It is given as in Henry per meters. Series inductance given by Henry per meters. So the shunt conductance is given by Siemens per meters. So the shunt conductance is the G value in here, where we have a parallel resistor. So the parallel resistor is giving us a conductance. 1 over R is conductance. So C is shunt capacitance. So that shunt capacitance we denote using farads per meters. Okay, so now the question is, why do we use these components to denote a transmission line? Okay, so the reason for using these components is to denote the real behavior of transmission lines and the loss of current and loss of voltage along the transmission line. So as you know, there are two conductors, top conductor and bottom conductor in this transmission line. So there's also some dielectric material in between these two conductor. There's some dielectric material in between these two conductors. This space is filled with dielectric material. Okay, this space is filled with dielectric material. But are there perfect dielectrics? Are there perfect dielectrics in this world? There are no perfect dielectrics in this world. So therefore, some kind of a leakage current is flowing in between these two currents. So the stray currents that flow from the top conductor to the bottom conductor are denoted by using the parallel resistor G. So this denotes the stray currents. This is used to denote the stray currents that are traveling through the top conductor to the bottom conductor due to the imperfectness of the dielectric material. Right, so the dielectric material cannot provide infinite resistance to the stray current, but it will have a finite resistance. Okay, so the dielectric cannot provide infinite resistance to the current, it will have some finite resistance. We denote that resistance using G. And then we have the shunt capacitance. Okay, so the stray current which is flowing through this top conductor to the bottom conductor generate a stray capacitance between these two conductors. So once the current is flowing from through this dielectric material, through this dielectric material, after some time, some capacitance, some voltage is getting generated across these transmission lines. So that voltage is denoted using this capacitance. This capacitance denotes the voltage that is generated between the two conductors due to the stray currents. Okay, so those are the two components that were included in this circuit that is included because of the effect of stray currents. Because of the existence of the stray currents, we have to include these two components. Then we have the normal circuit conducting current along the top conductor. Okay, so the current, once it is flowing in this transmission line, the current is a AC current, alternating current. The alternating current produces magnetic field. So in order to denote the magnetic field generation, an inductor is added to this series to this top conductor. So the magnetic field that is generated will be denoted or calculated or valued using an inductor. Okay, magnetic field generated can be represented using an inductor. The series resistor is used to denote the imperfectness of the conductor. Right, the conductor, the top conductor is not a perfect conductor. The top conductor is not a perfect conductor. It has a certain resistance, right? Not a perfect conductor. It has a certain resistance. So it has a certain resistance. So the top conductor resistance is basically shown by this resistor value. So not perfect conductor, because of the conductor not being perfect, we need to consider the resistance in that conductor. So that resistance is given using this series resistor value. So series R will give the series resistor value that denotes the resistance in the conductor. Okay, so there's some resistance to the current. So this is the circuit that we use to denote the transmission line, and it's the wave propagating through a transmission line. So we can use this circuit to understand how the wave will propagate through the transmission line under this effect of these kind of components. Okay, under the effect of these resistors, inductors, capacitors, conductances. What is the value? How does the electromagnetic wave propagate? What is the value of electromagnetic wave amplitude at the end of the transmission line? Those things can be defined using this transmission line circuit. Okay, so we can apply different laws to this transmission line circuit. Right, so since we have denoted transmission line as a circuit, we can use a circuit theory to analyze the circuit. So we can use the circuit theory to derive equations for the voltage and current in the transmission line. So using the using the Kirchhoff's current law and using the Kirchhoff's voltage law, we can derive equations for the current and the voltage in the transmission line. Current and voltage law can be used to derive the voltage and current and voltage in the line. Okay, so by deriving the current and voltage in the line, we can observe the behavior pattern of the current and voltage. Okay, so once we apply those laws, we can observe the behavior of the voltage and current. So through the calculations, it is seen that the voltage and currents are getting transmitted through this transmission line as a wave. That means the amplitude of the voltage is also changing as a wave amplitude. The amplitude of the current is also changing as a wave. So both current and voltage, they are behaving as a wave inside the transmission line. So after simplifications, it is seen that after simplifications using mathematics, it is seen that the voltages and currents are behaving. It is seen that the voltages and currents are following a wave-like behavior, and currents are propagating as waves inside the propagating as waves in the transmission lines. So therefore, their amplitude is varying as a wave. Right? Their amplitude is varying as a wave. The amplitudes are varying as a wave. Okay, so that is a new conclusion that we have come to regarding voltages and currents in the transmission lines. Okay, the transmission lines, when it carries high frequency signals or waves, then voltages and currents will behave as waves. So because of this, the transmission line has to be studied in a different way than we usually study it. Do you have any questions? Okay, so the voltage and currents. Okay, so the waves are propagating. The I mean, the voltages and currents are propagating as waves. So the wave-like behavior is seen uh, once we consider the transmission lines. So the voltage will move as a wave inside this transmission line. Okay, so this is you need to just assume that this is a wave. Okay, so the voltage will propagate as a wave. Similarly, current will also propagate as a wave. Okay, so until it reaches the load, the load could be an antenna. It could be something like it's a complex load, so it will have A plus JB kind of impedance. So it is a complex impedance. So the wave will propagate until it reaches the load. So once the wave hits this load, part of the wave will reflect back because of the most of the time because of the impedance mismatch between these two transmission line and the load, right? So if there's a mismatch, there is a mismatch between the impedances, then the T line impedance and the load, then the reflection will happen. A reflection will happen. A reflection will happen. A reflection will happen, and part of the incident wave, part of the wave which was incident into the load will reflect back. Okay, and part of the wave will be reflected back. Okay, so that because of that phenomena, we define parameters to determine the amount of reflection that happens in this transmission line. So that parameter, one parameter, we call as the reflection coefficient. Okay, so the reflection coefficient is a parameter where we use that parameter to denote the amount of reflected wave to the uh, uh, incident wave. Okay, so sorry for the delay. So the waves are propagating, I mean, voltage and current are propagating as waves inside this transmission line. So we use some parameters such as reflection coefficient to denote how much of um, voltage is reflected back um, from the initial wave. So we have parameters to define those using uh, the uh, equations. So uh, so I will just mention the equations. So the reflection coefficient can be defined as using tau. Tau is equal to the load impedance minus the characteristic impedance of the line divided by the load impedance plus characteristic impedance of the line. So the characteristic impedance of the line is the impedance of the transmission line. Okay, so the characteristic impedance of the line is generally a standard value. You can find it using some measurements. So you need to test, you need to do a test to find this value, the characteristic impedance of the line. So normally that line transmission, for transmission lines, for calculations, we take the value of 50 ohms as the characteristic impedance value. So this value is not the actually this is not applicable in all the transmission lines. So it will change to other values such as 33 ohm, 120 ohm. Likewise, it will change depending on the different application that we are considering. Depending on the application we are considering, the value of Z naught can change. But in general, we are using as the standard value of Z naught as 50 ohms. So if we know the amount of the value of the ZL or the load impedance, we know the load impedance, we can find the value of reflection coefficient at the load, right? The reflection coefficient can be measured at any point in the line. Okay, so the reflection coefficient can be measured at any point in the line. So if we try to find the reflection that is happening at the load point where the load is connected, then we find the reflection coefficient at the load. So the reflection coefficient at the load is defined as this um, tau L. Okay, so we define the reflection coefficient at the load using the tau L. Okay, so the reflection coefficient value can be some some complex value. Okay, and therefore the value of the tau L can be denoted as a magnitude and a phase. So we can denote the value of tau L using phasor representation. So the value of tau L can be given as the magnitude of tau L into e to the j theta. So where the e to the j theta denote the phase component of the tau L value. So we can denote tau L as a complex value and then we can turn it into the phasor domain. So the phasor domain value of the tau L is given using this expression. So the phasor domain representation of tau L can have magnitude and its angle. Okay, so the tau L value could be a complex number. So tau L value is used by us to understand how much of reflection happen in the system, how much of reflection happen at the load. So depending on the reflection that we see, we design our systems to reduce the reflection as much as possible because we don't want to get our wave reflected back. So we need to reduce the reflection. So the solutions that that we are going to do for this is what we are trying to do as engineers. So there are main methods to reduce the reflection. So in this module, you will be just understanding that there are parameters like this, reflection coefficient. Other parameters are also there that are used to understand the amount of reflection. Okay, so apart from that, now I drew this wave. So this wave is the forward wave or the incident wave. Okay, so the wave which is going initially towards the load, we call as the incident wave. Incident wave. And the wave that gets reflected back after the incident wave reaches the load is known as the reflected wave. So the reflected wave could be of a smaller amplitude than the initial wave. So we can have a wave which is of smaller amplitude than the initial wave. So we can have a wave wave which is of smaller amplitude than the initial wave. So the wave, let's say the frequency of the reflected wave is also the same of the same as the incident wave uh, uh, frequency, just the amplitude is smaller now. Okay, so the amplitude of the reflected wave is reduced, and the reflected wave uh, is uh, denoting us how much of energy has been lost. Okay, so we have lost some energy, and some uh, uh, the remaining wave, I mean the part of the wave which is getting reflected back is shown as the reflected wave. So other part of the wave has been consumed by this antenna. It has consumed most of the energy, but the rest of the energy has been reflected back into the circuit. So the reflected wave is having a different amplitude than the incident wave's amplitude. Okay. If you have any questions, you can ask. I will erase. I will erase this. So the characteristic impedance, characteristic impedance is the impedance value that denotes the impedance that the transmission line has to the wave propagation. Okay, so the impedance that the transmission line imposes on the wave propagation, imposes on the wave that is getting propagated, right? So there's a wave getting propagated. So the transmission line imposes some impedance to the wave propagation. That value is given by Z naught, right? So Z naught value is normally a standard value, but we can also find it using the ratio between V naught plus and the I naught plus. So the V naught plus is the incident waves voltage amplitude. Okay, so the voltage value, voltage amplitude of the incident wave is given by V naught plus. Okay, so this is regarding incident wave. Okay, so incident wave voltage amplitude is V naught plus, and the incident wave's current value, current amplitude is given by I naught plus. Okay, so we take the ratio between the incident waves, voltage and current to find the Z0 value. Another way to do is by taking uh, the ratio between the reflected waves amplitude over the reflected waves current. Okay, so the reflected waves are given by minus signs and there's a minus sign in the front. So that minus sign is only denoting that the voltage is uh, moving in the reflected direction. So anyway, what you need to do is you need to take the ratio between the reflected waves amplitude, voltage amplitude and the current amplitude and uh, take its value. Okay, so the so in here the minus sign is only denoting the direction of the wave propagation. So you need to not consider that as the minus sign of the current. My current is not a current is behaving differently in this circuit. It is not going in the minus direction. Current is, I mean, yeah, it is going in the opposite direction to the incident direction, right? So the current, when it is moving in the reflected direction, it is also going as a wave in the opposite direction. Okay, but in this circuit we do not have the current changing its direction as in the usual circuits where the direction of the current is changing and from the initial direction. So the current will move as a wave. Current will move as a wave. Voltage will also move as a wave. Voltage will also move as a wave. So there could be a different voltage, I mean amplitude for the voltage, and that voltage will move as a wave. So there could be a different voltage amplitude and it will move as a wave. So that is regarding how we can find the voltage and currents in the reflected directions. So they are all moving as, I mean, waves. And this minus sign is added to represent the minus direction of the wave propagation. You can find the amplitude of the voltage and amplitude of the current and take the ratio uh, to find the Z naught. So you can just get the reflected voltage and reflected current and find the ratio. So so let's so that is regarding the Z naught value. So when we talk about the reflection coefficient is the parameter that define how much of reflection happen in the circuit. So if we take the reflection that is happening at the load, we can take three cases. We can take basically three cases where the reflection where the reflection can happen. Three extreme or special cases. So we can take three extreme or special cases. Or special cases. And we can take those cases as a no reflection case, and open circuit case, where the transmission line is open circuit and the transmission line is short circuit. So short circuit case. So we can consider three cases to study the reflection of the transmission line. Okay, so under these conditions, we study the reflection and how it happens. Based on those behaviors, we can identify what might happen in the intermediate scenarios. So the no reflection case happens in situations where we don't have any reflection. So we don't have any reflection at what incidence? We don't have any reflections when we have fully matched case. Fully matched case. Fully matched case. When we have fully matched case, we don't have any reflection because our impedances are fully matched. So impedance has been fully matched. So that means that the impedance matching has been done. So in that case, we don't face reflection. The reflection will be very minimum. In that case, the reflection coefficient will be 0. So reflection coefficient will be 0 in this case. Okay. And then if we have open circuit at the end of the line, then that means we have a very high impedance at the end of the line. If we have high impedance in the end of the line, then the impedance at the end of the line will be reaching infinity, right? The impedance, load impedance will be reaching infinity. If that is the case, then what is the value of the reflection coefficient? So since we cannot divide infinity by infinity, we need to simplify this reflection coefficient further to find the value of the reflection coefficient in this occasion. So we need to divide each component of this parameter in this equation by ZL. Once I divide each of these parameter by ZL, I can get 1 plus Z naught over ZL. If that is the case, then I can find that once the ZL goes to infinity, the final value of tau L is going to equal to 1 plus 1 plus 1. And then if we face a short circuit condition at the end of the transmission line, then the value of the reflection coefficient will be equal to minus 1, right? So the reason is now ZL is going to be 0, right? ZL is going to be 0. So 0 minus Z naught divide by 0 plus Z naught. So therefore, the value of tau L is going to be minus 1. So if you have any questions, you can ask. Okay, so what do you mean by how to reduce amplitude? I can't understand your question. We are not trying to reduce amplitude in the system. Our amplitude gets reduced because of the mismatch in the impedance between the transmission line and the load impedance. So we cannot prevent it, but we need to prevent it by, we can prevent it. Initially we need to first observe what is the reflection that is happening in the system. And based on the reflection coefficient that we calculate for the system, we can decide the best impedance matching technique that we can use. So finding the reflection coefficient is important in that case. And we can use tools like, as I said before, Smith chart. Right? We can use the tool like Smith chart to match the impedance of the load to the transmission line. So the Smith chart, I will explain a little bit about the Smith chart. So the Smith chart is a chart of which has a circular shape, and it can be used to denote the impedance of a transmission line at any point in the transmission line. So apart from that, we can find the reflection coefficient that happens in the transmission line. If we know the reflection coefficient, we can denote it in this Smith chart. After denoting this reflection coefficient in this Smith chart, we can follow some steps to find the optimal position where the reflection coefficient will be 0. Right? We can design some additional components to be added to the circuit using this Smith chart. So the Smith chart will have like circles, and it will have some geometric shapes. I will show you a Smith chart later. So the Smith chart is used to match the output impedance, the load impedance, to the transmission line by following some steps, some pre-known steps. So we can move the reflection coefficient to another location using this design, or Smith chart based design that we do. So we can use the Smith chart to do the matching. I will show you a Smith chart later. So now I will just discuss with you regarding the transmission line types. So there could be transmission lines which are lossy and which are lossless. So in most of the cases, we are considering the case where we have a lossless transmission line, right? And we do not consider the lossy transmission lines in most of the cases. So the reason is that once we are sending very high frequency signals along the transmission line, we assume that the amount of attenuation that happens per unit length is considerably low. So the attenuation is happening, but the attenuation that happens is considerably low. So therefore, for high frequency signals, we are considering that the transmission lines act as lossless transmission lines. Okay, so based on that assumption, we are doing the rest of the calculations for the transmission line, right? So apart from that, once we are considering the attenuation aspect of the transmission line, we have basically a constant that we call as the propagation constant that we denote as using gamma. Right? Gamma is equal to alpha plus j beta. Right? So alpha is known as the attenuation constant. Attenuation constant. And the beta is known as the phase constant. Right? So the propagation of waves inside a transmission line can be denoted using this propagation constant. So the propagation constant can be used to denote the attenuation of the waves in the transmission line. So the attenuation constant in a lossless transmission line will be 0. Attenuation consider in a lossless transmission line to be 0. So alpha value will be equal to 0, and only the beta value will have a certain value. Okay, so so basically in our calculations we consider situations where beta value has a certain amount. So the input impedance of the line, of the transmission line at each point is important for us to match the transmission line to the load. So the transmission line is connected to a certain load, and in order to match the load to the line, we need to know the impedance at each point in this line. Okay, so at each point in this line, we need to know the impedance. In order for us to find that value, we use a certain equation, right? So the impedance that we see, for example, at a certain location in the transmission line, we denote as the impedance seen across these two conductors. So if we, for example, if we take this location, we try to find the impedance between this location in the line. That impedance value can be found using this equation. Okay, so this equation is equal to Z naught into ZL plus JZ naught tan beta L divided by Z naught plus JZL tan beta L. Okay, so this is the equation that we use to find the impedance at this location, where L is the length from this load point to this point. L is the length from this load point, right, where we connect the load. We neglect this, length that we use to connect the end point of the load to the exact, load, which is the antenna or something, right? So we consider that the impedance of these lines are concentrated in the load in here. So the length in here is negligible. So the length from this point where we connect the load to the transmission line and the point where we observe the impedance is given as simple L. So using these parameters, we can find the input impedance at this line, right? So we said naught, we know, we said L is the impedance of the load. I said L. I said naught is the impedance of the transmission line, and beta L. Beta is the phase constant, right? That I mentioned just now, right? So the phase constant. So the phase constants can be found using an equation where we take the 2 phi over lambda. 2 phi over lambda. So if we know the so if you can remember, 2 phi over lambda is also equal to the wave number that we defined earlier. So beta is also same. The difference is beta is used to denote the value, similar value in the transmission lines. So you take the ratio between 2 phi over lambda when you want to calculate the beta value. So beta value can be found if you know the value of lambda. The lambda value can be found if you know the value of frequency, right? The frequency, so C equals F lambda, right? So using this expression, you can find what lambda is, C over F. You know the frequency of the line, of the wave that is transmitted, then you can find the value of lambda using those relationships, you can find the value of lambda, and using that you can find the value of beta. So since you know all the values in this expression, you can find the value of the input impedance at any point in the line. Okay, so the L value is measured from the load towards the source. If you have any questions, you can ask. Okay, so then I'm going to describe another parameter that is used to define the transmission lines, which is known as the voltage standing wave ratio. Voltage standing wave ratio. Okay, voltage standing wave ratio. We denote it using VSWR. Voltage standing wave ratio, VSWR, is defined as the ratio between the voltage maximums of the transmitted and reflected waves. Okay, so it is defined as the uh, ratio between the voltage maximum that you observe and the voltage minimum that you observe in the transmission line. So the voltage ratios between the transmitted lines, transmitted voltages, transmitted or incident wave, um, so between transmitted and reflected voltage standing waves. No, so actually this is the ratio between the voltage maximum and minimum that you observe in the transmission line once you observe a standing wave in the line. So I will explain that. Okay. So now we are considering the scenario where we are having a transmitting wave, incident wave on the load, and there's a reflected wave coming back from the load, right? So after some time, the voltage and the current waves that get incident on this load and that get reflected back superimpose, or else they add together. Okay, so what happens is that if I send a certain voltage signal to this load, this voltage value, some part of the voltage value will get reflected back, right? So some part of the voltage value will get reflected back. So after some time, both of these reflected and incident waves will superimpose or add together. So both the incident wave and the reflected wave will add together, and reflected wave will add together. Okay, so both these waves will add together. Okay, so once the waves add together, a standing wave is created. Right, a standing wave is created. So which is like a wave which does not appear to change with the time. That is the reason that we call it as a standing wave. The amplitude and the frequency of that wave, that wave remains constant with the time. So So a wave whose amplitude and phase remain constant over the time, we call as a standing wave. So this standing wave is caused due to the addition of both the incident and the reflection waves, right? Addition of incident and reflection waves. So this is the incidence. I mean, due to this addition between incident and reflection waves, the standing wave is created, which is not changing over the time. That means it's like amplitude and its frequency, its phase does not change over time. The that wave is constant and generated in a constant manner in the transmission line. So we can measure the maximum voltage that we can observe in the standing wave, and we can observe the minimum voltage that appears in that standing wave. So the ratio between those two values give the VSWR value. Okay, so that VSWR value we can also find using the value of reflection coefficient. So if we know the value of reflection coefficient at the load, we will use the reflection coefficient at the load here. So we can find the VSWR value, but by taking 1 plus magnitude of the reflection coefficient divided by the 1 minus magnitude of the reflection coefficient. So this will give us the VSWR value. So if we have the value of the reflection coefficient, we can find the VSWR value, right? So VSWR value can vary from a value of 1. It can vary from a value of 1 to infinity. Okay, so the reason is that if we have a situation where we have the reflection coefficient 0, if we have our reflection coefficient 0, then VSWR value is 1. If we have the reflection coefficient as either 1, right? If the reflection coefficient is 1, plus or minus 1, then the magnitude of the reflection coefficient will be 1, right? That is the case, then VSWR will be 1, 2 over 0. So in that case, the value of VSWR will be 2 over 0, which is infinity. So in cases where we have reflection coefficient plus 1 or minus 1, which occurs during short circuit and open circuit cases, I mean, open circuit case, during open circuit case, we have, reflection coefficient equal to plus 1. And in short circuit case, we have it as minus 1. So in those cases, we have the VSWR reaching up to infinity. So these parameters are used to understand how much of voltage difference is there between the voltage maximum and voltage minimum. So what we try to do is we try to make the voltage maximum and voltage minimum as equal as possible. We try to bring the maximum value and minimum values to similar values as much as possible. So VSWR is another parameter that we can use to measure the reflection in the line. Another important thing that is related to transmission line is the power delivered to the load. The power delivered to the load. Right. So I think you have discussed about power delivery to loads in other modules as well. Right. So from a circuit to a certain load, the amount of power that can be delivered in average can be given by this equation. Right. So we can take the real part of the voltage value and the current value, its conjugate, and we can take the real part of this VI value across the load, and we can take the half of it to get the average power delivered to the load. Okay, so since we are considering electromagnetic waves, we cannot define a certain amplitude or a definite amplitude to these voltage values and current values. Right, so this is not a DC circuit. So since the value of voltage and current is changing with the distance, we denote the voltage and current using VZ and IZ. So in terms of Z, the voltage is varying and the current is varying. And we are multiplying the voltage and currents in this manner to get the, maximum multiplication between voltage and current, right? So once we multiply the voltage with the conjugate of the current, we can get the, square of the, the voltage and current values, right? So we can take the maximum output that can be obtained using the voltage and current by taking this multiplication between the voltage and the conjugate of the current. Then we can denote the this equation in different manners. So finally we can get an equation. I'm not going to do the derivation, but I will give you the final result, where the derivation will give us the result as the amplitude of the incident waves voltage divided by the characteristic impedance of the line into 1 minus the reflection coefficient of the line, reflection coefficient of the line into the squared of its value. So if we know the reflection coefficient of the value at the load, then we can find the value of the power delivered to the load. So the reflection coefficient of the value denotes how much of power is reflected back into the circuit. So 1 minus of that value gives us how much of power we have given to the circuit, given to the load. So we are, therefore, that is why this equation has this 1 minus tau L squared. Okay, so just as normal circuits, we will be taking V squared over R as the power, but in here, additionally, we need to multiply it with the 1 minus tau L squared to take into the effect of the reflected wave. Okay, so V in here is the maximum amplitude, or the maximum amplitude that we can observe in the incident wave. Okay, so that is basically regarding power that is delivered to the load. Okay, if you have any questions, you can ask. So related to transmission lines, that's all I'm going to cover. And then I'm going to discuss a little bit about the the antennas. So the frequencies are equal in the reflection and incident waves. So they are equal in the incident wave and the reflection wave. So the apart from that, the voltage and current are also in phase. So the reason that this is happening is that I'm answering the question that is given to me. So the voltage and current, voltages and currents in the lossless lines are in phase. So therefore, the frequencies of voltage and current waves in the transmission line are in phase. So they are adding together. So voltage separately will add together its incident wave and its reflected wave. The current will add its incident wave and reflected wave. So these frequencies will be similar between the, in the incident and reflected waves, mainly because the line that we are considering is a lossless line. So because the lossless lines, the amount of frequency change between the incident and reflected waves is minimum. So both are in phase. So I hope those are the questions you had, and I hope I answered your question. Now I will discuss a little bit about the antenna. So you have to discuss, you have to learn a little and a little bit about the antennas, but not in depth. Okay, so I will give you a certain no, but I think there's not much time. So in all my lectures, I discussed about the antennas and how we can generate alternating current in the antennas. So the antennas are supplied. The antennas are connected to a certain power supply, AC supply, using transmission lines that we discussed, and the antennas are radiating energy from its metal conductors. So the antenna length is very important when designing the antenna radiation. So antenna radiation will happen only if we keep the antenna length at a certain specific length. Okay, so in here I'm going to discuss about the specifically about the dipole antennas. And under that dipole antenna, we have the half wave dipole antenna. So I'm going to discuss about the half wave dipole antennas. So half wave means lambda over 2, right? So half wave means lambda over 2. So lambda over 2 dipole antenna means the length of the dipole antenna is lambda over 2. Right? So the length is maintained up to lambda over 2, mainly because if we do not have that length, we do not have the radiation happening in the most optimal manner or in the most maximum way. So in order for us to add the radiation that happens through the two antenna arms, we need to have the length of the antenna in the lambda over 2 length. Okay, so in the antenna we have two arms, one arm and second arm in here, right? So as I said before, we can connect this antenna to a power supply using coaxial cables, right? So there are two conductors in the coaxial cable. One conductor can be connected to one arm of the antenna, and another conductor the remaining conductor can be connected to the next arm of the antenna. And then if we have lambda over 2 length, the voltage that is occurring in this antenna will be of this form, right? So the voltage will form in such a way that the voltage will be maximum along the edge of the antenna arm. Okay, at the top of the antenna arm, the voltage will be maximum, and in the bottom arm, the same wave will be generated. Voltage wave will be generated, and it will have a voltage where the voltage maximum happens at the bottom end of the conductor. So voltage maximum happens here. Voltage maximum happens here. Voltage minimum happens here. So since these voltage patterns are like complementary or like supporting each other, radiation will happen uh, successfully by these two arms. So the radiation will happen by these two arms to the uh, to the space as much as possible. Also, like the current, the current that we are producing will be alternating current. So the current will be going up and down. So the current will be going up and down. So the magnetic field that is generated through this through these antenna arms will be generated in a uh, manner such that the uh, magnetic field is generated around the arms of this antenna. So magnetic field will be generated around the arms of this antenna, right? So the magnetic field will not be created in this point where it is along the axis of the antenna. The antenna has the axis, right? Antenna axis. So the magnetic field will not be created along the antenna axis. In that axis, there will not be any radiation. No radiation along the antenna axis. Antenna axis. So the radiation will only happen around um, the uh, the other regions of the antenna. Okay, so apart from that, is uh, it is shown that the uh, radiation uh, will flow around the antenna as a sphere, right? However, it is since the radiation does not appear uh, along the axis where the antenna along the antenna axis, uh, along that axis there will not be any radiation. So the total radiation will be according to a donut, like a donut like shape. So we can draw that as well. Okay, so the antenna radiation will happen in a donut manner, donut shape. Okay, so the radiation will happen in this manner. Radiation will happen in this manner. The radiation will not, radiation will happen in both the directions, right? Or both in like the one side of the antenna and the other side of the antenna. The in this region between the two spheres, there will not be any radiation. So there will be like a null area where the radiation is null. So the in here there's a hole. So in that is why the radiation is known as a donut shaped radiation. So we have radiation as a donut. So all around the antenna in 360 direction, we have the radiation as a donut. So the radiation around the antenna as a donut. Antenna will be shaped like a donut. Is So if we do not use the length of the antenna exactly as lambda over 2 or very close to that, then what happens is that the antenna length will be lambda, so lambda over 2 on both sides. So the wave pattern that will get generated in this situation will have will generate the voltages in this kind of a manner, where the voltage maximum will happen at the end point of the antenna arm, but also the voltage, voltage 0 point will happen in an intermediate location, and there's another voltage maximum happening at the feed point of the antenna. Same thing will happen in the lower arm of the antenna, and the voltage maximum will happen like this, and voltage minimum will happen, voltage 0 will happen here, uh, voltage will be uh, reverted, and maximum will occur in this feed point. So due to this, I need to draw it in certain way. I need to draw these two waves must be symmetrical. Okay, so these two waves that are generated in the arms 1 and 2 are symmetrical and equal and symmetrical. So this voltage and this voltage will cancel out, and this voltage and this voltage will cancel out, and therefore there will there will be no radiation if we select the antenna length to be lambda. The antenna length to be selected as lambda, for example, there will be no radiation because of the cancellation of the voltages on the both sides, on the both arms. So that is regarding the antennas and dipole antenna basically. So it's very important to design the antenna with the correct length. So we need to design it with the correct length in order to get the radiation as we expect. Since we want to give a high radiation as possible, we need to design according to the standard antenna lengths, and then we can get the radiation. So this is regarding antennas, dipole antennas. If you have any questions, you can ask. So for today's lesson, that's all I have. So I will ask questions from each content that I have covered in the class to the exam. The end exam will be a close exam. So close book exam. Then so you need to prepare accordingly to prepare for this exam. So so by this lesson, I'm going to finish the content that I have for the electromagnetism. In the next class, you will be having your mid exam. So after that, we won't be having any other lectures. You will have your study leave, and you can continue with that. If I have any announcements or any information that I want to give you regarding the end exam, then I will inform you via LMS or and also the WhatsApp. So end exam will happen in this week on Wednesday. So sorry, mid exam. Mid exam will happen on this Wednesday. So between 3 to 4 in the OD1. If there are any changes, I will let you know. So you need to register for the midday exam. Only those students will be allowed to participate. Okay, so that's all for today's lecture. So if you have any questions, you can ask. Otherwise, you can leave. So thank you for attending. if I'm giving equations, I will let you know beforehand.